Hello and welcome to today's video. In this video, we're going to take a look at an application of continuity. In particular, we're trying to approximate the root of a continuous function over a given interval. This method is called bisection, and that's also the title of this section, the bisection method. And as I said, the idea is to approximate a root of a continuous function. Now, the nice thing about this is we don't have to know a lot about the function. Basically, the only thing we need to be able to is to compute values for given input points. And we need to be sure that the function is actually continuous. Not a lot more is necessary. On the other hand, we don't gain a lot as well. This is an approximation. It doesn't necessarily give us the root, but it just approximates it numerically. It's pretty fast. It gives us an approximation very fast. But it will just approximate one arbitrary root. So we don't have any control about which root it does approximate unless we know beforehand where the roots lie approximately. It doesn't give us any information about how many roots the function will have, and we can't choose one if it has more than one root. So I'll give you the details right away. Let's go into that procedure. And I'll illustrate that by a small example afterwards. So as the input for that procedure, we'll require the following. We'll require first a compact interval. So remember, compact means closed and bounded, so the interval has the form AB for arbitrary or suitable values of A and B. We'll also require a continuous function on that interval. With values in R as usual. And we want that function to have the following property. F of A should be negative, while f of B should be positive. So then, due to the intermediate value theorem, we can be sure that every function value between f of A and f of B is actually assumed by the function f. So in particular, the function value 0 will be assumed. So the function actually has a root. Okay, so the consequence of this is f has a root. Let's call that x star, with f of x star equals 0 in the interval AB. And finally, as the last part of the input, we want an acceptable error, an acceptable absolute error to be specific. And we call that epsilon. So we'll usually not be able to find the actual root of the function, but we will approximate it to a given tolerance, and that tolerance is the error epsilon. So I want to be at least that close to the actual root. And that's specifying the output. So output of that procedure is going to be a point x star in the interval AB with f of x star equals 0. So that could be one possible output. We could actually obtain the root or one of the roots. Or, as an alternative, we get at least an interval that contains that root. And we'll denote that interval as delta minus, delta plus. And that's going to be a subset of AB, of course, such that delta plus minus delta minus is less than epsilon. So the interval is going to be small, and this interval contains a root. So we might not obtain the point itself, but we obtain a small interval that contains it. Now the procedure proceeds as follows. It starts by setting the initial interval, delta minus, to the point A, delta plus to the point B. So we start with the original interval first. And then, as I said, by the intermediate value theorem, we can be sure that this interval contains root of f. By the IVS. So IVS is the intermediate, or IVT, sorry, is the intermediate value theorem. Two, now let's check if the interval maybe is small enough already. And if it's not, we're going to refine it. So while the interval delta plus minus delta minus, while the size of this interval is still too large, and too large means it's greater or equal to epsilon, we repeat the following steps. The first thing we do is we compute the so-called bisector, and that is where the method gets its name from. And this bisector simply is the middle of the interval. We call that gamma of the interval delta minus to delta plus. And gamma is simply defined as delta plus plus delta minus divided by 2. So what that is that is the middle of the interval, the midpoint. And now there's three possibilities. We compute the function value at gamma, and either the function value is 0, then we've hit the jackpot, and we can just return that gamma as our x star. So next step we do is, if f of gamma happens to be 0, then stop, and return x star as gamma. Otherwise, if that's not the case, the function value at gamma is either positive or negative. If f of gamma is positive, then, well, what do we know? Remember that we started with an interval that has a here, and you remember f of a was negative. And then we have b here, and you remember f of b was positive. Now if f of gamma is positive, gamma is the midpoint of the interval, so here's gamma. If f of gamma is positive, right, then that means we can be sure that there is a root in that part of the interval here. Right, it's negative here, it becomes positive here, so 0 must be crossed somewhere here. There might still be a root here, but we cannot be sure. We can't be sure about this one, so what we do is we cut the interval in half, and we just take this here as our next interval. So if f of gamma is positive, what we do is we set the right boundary to gamma. Set delta plus to gamma. What could also happen is maybe f of gamma is negative. So what if f of gamma is negative? Well, if it's negative, then we can be sure that there is a root in this part of the interval, because it's negative on the left and positive on the right. So what we do is we just keep this half of the interval. And that means we have to change the left boundary of the interval. We keep the right boundary. So third possible case, if f of gamma is negative, set delta minus to gamma. And then we continue with the next step. So either the interval is now small enough, or we go on, we compute the bisector of the next interval, and so on and so forth. So that's all there is to that procedure. And you can see the interval is cut in half every time. So basically, we're approaching the required size very quickly. A quick example just to illustrate how this works. I'm not going to give you all the computations here in detail. There'll be examples on the exercise sheet that you can use to practice that with maybe more amenable functions. And of course, in practice, you'll usually use a computer or at least a pocket calculator to compute the function values. And as usual, if that's going to be on the exam, then the function value should be easily computable. That might not be the case here, but just for the sake of an example, let's have a look at the function 2x minus 2500 minus x to the power of 2/3. So that's the third root of x squared. Now this is a composition of continuous functions. So the first thing we need to note is this function is continuous. We want to find a root, or at least approximate a root of f. And the next thing we need to do then is we need to find an interval, AB, that contains such a root. And for that purpose, we'll just have a look at arbitrary, more or less arbitrary function values that we suspect might contain a root. We'll start by computing f of 1000. And you can see this is 2000 minus 2500. That's negative already. Minus the third root of 1000 squared. So 1000 squared, that's easily expressed as 10. So 1000 is 10 to the power of 3. That means 1000 squared is 10 to the power of 6. And then the third root of that is, of course, 100. So what we get here is minus 500 minus 10 to the power of 2, that's 100, so we have minus 600, and that's obviously negative. So we found the negative point. Let's see if we can find a positive point as well. And to do that, we will try 3000. You can see this is 2 times 3000 is 6000, that's minus 2500, that's still positive by quite some amount, minus the third root of, now 3000 is 3 times 10 to the 3. So the square of that is 3 squared times 10 to the 6. And that means what we get here is, again, this 10 to the 6 will give us a factor of 100. And then we have this factor of third root of 3 to the power of 2. Now that's less than 3, so this whole thing here is less than 300. And that means 6000 minus 2500 minus something that is less than 300, that is certainly going to be positive. So we do have our starting interval already. And that means we start the bisection with delta minus, delta plus is 1000 as the left bound and 3000 as the right bound. Okay, so we have 1000 here. We have 3000 here. We know f is positive here and f is negative here. So the next step is going to be computing the bisector. Now the bisector is the middle of this interval. Now that's easily computed, of course. That's 3000 plus 1000 divided by 2. So we get 2000, right? That was obvious, hopefully. The midpoint of that interval is 2000. And now we have to evaluate f on that interval. So what do we do? F of 2000, well, that's 2 times 2000, that is 4000, minus 2500, minus the third root of 2 squared times 10 to the 6. And again, with the same arguments as before, this here is now a little less than 200. So we can be sure that it's still greater than 0. We don't even have to compute the actual value. We just need to know the sign of that expression. So here, f is greater than 0 here. And that means we can be sure there is a root in this left part of the interval. So what we do now is we set the new interval by updating the right bound. We move that right bound down to 2000. So we keep this part here. So the new interval, delta minus, delta plus, is now 1000, 2000. And again, we compute the bisector. I'll just give you this last step here. The bisector gamma is now, well, 2000 plus 1000 divided by 2, that's 1500. So next step is this next bisector is here, 1500. And again, we have to compute the value at that point. Or at least we have to find out whether the value is positive or negative. Now here we have 3000 minus 2500, that's 500. So we're getting closer to 0 already. Minus the third root of, well, it's 1.5 squared times 10 to the power of 6. So what we get is something like 1.5 squared, third root of that to the power of times 100. So we can be reasonably sure this is less than, let's say, 200. And that means we still have a positive function value here. So f is still positive here. And again, we update our interval. We move the right bound. In this case, we keep this part here, right? From negative to positive. So this is the interval that we want. So that means new interval is now delta minus, delta plus. The interval from 1000 to 1500. And you can see we've gotten down to an interval length of 500, but we started with 2000. So we halve that in each step. We started with a length of 2000. We go down to 1000. Now we're at 500. In the next step, we'll be down to 250. So we approach the desired arrow bound pretty quickly, hopefully. So I'm not going to show you the following steps. It just continues in the same way. Next, we'll test 1250 as a new bisector, see if the value is positive or negative, and then again, keep the appropriate interval. So this is how bisection works. Again, there'll be examples of this on the exercise sheet. Now this concludes our treatment of continuous functions for now. In the next steps, we're going to add something on top of continuity, and that's going to be differentiability. But more details on that will be in the upcoming videos, and as usual, I hope I'll see you then.